Hey, my friends, welcome back. This is lecture 23 for CSE 1322, and sadly, I know you are all going to be devastated. This is the last lecture where I'm going to cover new material for the semester. After this, you are going to be dealing with just the review lectures, which will come up. So this lecture is technically for the week before Thanksgiving. Many of you may watch it ahead of time. I wanted to go ahead and get it out there so that you guys can knock this out if you have extra time before Thanksgiving or whatnot. So this is the last of the lectures related to data structures, which is, of course, this last module in the class. It's module number, it's module number 9. That's the right number. Okay, so we have so far talked about linked lists. That was the first of these 3 lectures. And we discussed the idea that a linked list is just a node. The node has some data, and then maybe it has a next pointer. Then we used linked lists and arrays, an array list to some extent, to implement queues and stacks. And you'll remember the important thing about a stack, pancakes, is that first one that goes in is going to be the last one that comes out. And in a queue, the first one that goes in is going to be the first one that comes out. We looked at how to implement those with arrays, how to implement those with linked lists, and so on and so forth. All of those data structures that we've so far talked about are linear in nature. We think of them as a straight line. An array we think of as a straight line, right? We usually draw a box and we divide it up into 10 or 15 or 100 or 1,000 cells, and then we put numbers into those appropriate cells. A linked list we also think of as a straight line. There's the head pointer or the top pointer or the front or whatever we want to call it, and it connects you to the first node, which is then connected to the next node and so on, and you think of that in a straight line. So these are all linear data structures. But as I've mentioned when we were going through all of this, the big O notation, or the way of measuring the complexity of having to do things in each of those data structures varies, but in the best case scenario, it's order 1. And most of the time what we came out with was order n. And what that meant was, for a linked list of 100 entries, it's going to on average take 100 operations to look for a particular number in there. Is it really going to take 100 every time? No, of course not, because you'll probably find it halfway through on average, but you're discussing what is the case, the worst case scenario when you're doing a search in there. That's what big O is really a measure of. So can you do better than order n? And the answer to that question is yes. There are a number of different data structures that we're going to talk about today that are faster than order n. And so we're going to discuss ideas where you have data that's being stored in a way that is not linear for the first time. We're going to deal with things where they are connected in different ways. And if you think about this, that's kind of how the world actually really works. So I'm here in the Marietta campus, and there's a circular road that goes around the campus. And then there's all these little offspring roads that connect you to various different places. But you can drive all the way around that circle. There are many different paths that connect between each of the buildings. And whether you're here or whether you're in the Kennesaw campus or whether you're somewhere in a bizarre random country surrounded by cows and old people, in all of those cases, there is more than one way that you can get from one part of town to another part of town, or from one part of campus to another part of campus. The reason that we do this in the real world is because it turns out you're not always going from point A directly to point B. Sometimes you need to go from the dorm room to the student center to pick something up and then head over to the atrium building in order to actually go to class. Or sometimes you're at home and you need to stop at the gas station before you go to the grocery store or whatever it is that you might want to do. So if there was only ever one point connection from every item, it would be very inefficient to get anywhere. So the real world is more of an example of a graph, where lots of things are connected to each other in many different ways. From your home, there is likely, once you go to the end of your driveway or the end of the entrance to your apartment complex or your dorm room, there is likely a road that then connects to many different roads in a couple of different places. So if we were to draw out a typical city, you would not see a linear data structure. I cannot make that go away. All right, sounds good. You would see something like, so here's your home, and you have some road that comes out of your home, and then maybe that road forks off into 2 different paths. And then each of those paths may have roads that connect off of them in various different ways that in turn may have roads that connect off of them. And in reality, that's probably much more what your world looks like. And in some cases, you may have bizarre intersections, or you may have a roundabout, which then connects to four different roads separately. And so this is the idea of a graph, where you have connections from different parts of the information to other parts. So if you're putting this into perspective, this might be your grocery store, this might be your gas station, this might be where you work, this may be your kids' daycare, this may be your church or whatever else. These are all different places, and you can see that there's more than one way to get from your home to any one of those places. You can do a direct path, or you can do an indirect path, and in some cases, and I didn't really draw very many of these connections in, but I'll just connect a few more of them just so that you have, that was supposed to be a black line, just so that you get my point here, which is that there's very often many different paths that will actually get you to the same place. So home can go straight down to this node, or home can go up here and down and back around, or home can go over, up, around, down, and back around. And you're used to this concept. There are many different paths out of each node, and those connect in various different ways, giving you flexibility in how you get from point A to point B. This is called a graph. The most generic of the terms is graph. A more specific version that you might have is what's called a tree. The difference between a graph and a tree is that any one node can be connected in cycles in a graph, whereas in trees, they cannot have any cycles. So what is a cycle? Well, if I go to a red marker, this is a cycle. I can start off at home, I can go down this path, I can then go up this path, over this way, up this way, back down here, and I can end up right back where I started. There is effectively a circle that can be done on the graph, or a cycle. This is very bad from the standpoint of an algorithm, because if I was asking you to calculate every possible path that you have from your home, you have to be able to detect that you've been there before. If you have ever had a circumstance in your life where you're driving around in a new city and you don't know exactly where you're going, if you pass by the same point more than once, you eventually start going, oh, I'm going around in circles. That's because you're smart and you're a human being and you can detect that you're going around in circles. For a computer, that's not quite so obvious most of the time. So it needs to be able to keep track of, did it go in a cycle? Now you might be saying, well, when would a computer be doing this? So think about this. FedEx, UPS, DHL, whoever your favorite carrier is for delivering packages, they may have a map that looks something like this, where instead of home, it's the FedEx office, and the places that need to have packages delivered today might be here and here and over here. Well, what's the best path, the most efficient way for the driver to get from the office to those three homes? Well, that's a topic that a computer actually has to solve, and each of the major delivery providers have these algorithms that tells the driver exactly which way to go. Just taking it out a notch, Google Maps or Waze or Apple Maps, they all do this exact same thing. When you say, I want to go to this address, there are often millions of separate ways that you could get there. Some of them are completely bizarre, right? I want to get from the KSU campus in Marietta to the KSU campus in Kennesaw. A completely valid way to do that is for me to drive south on 75, get on I-20, drive to Los Angeles, go up to San Francisco, cross all the way back over to New England, come all the way back down, and end up in the Kennesaw campus. It's probably not the most efficient way to do it, but it is a valid path between those two. And actually, it has to decide, is that the best way? Obviously, it's not. Obviously, there's a faster way, but when you start factoring in traffic and weights on all of these paths, you can quickly imagine how it may be that the most direct path is not the best path, because it may be that there's a traffic jam or an accident that has closed some part of it, or there's roadworks or whatever else, and so it may need to send you some other way. Okay, so a graph is a real thing that exists in the real world, where you have connections that sometimes are cyclical and go around and allow you to get to the same place in multiple different ways. Traversing a graph from a computer science standpoint is a difficult task, because you have to be able to tell you've been there before, and you have to have some understanding of which path is what people want out of it, because even though there's many ways to get there, one of them may be faster, one of them may be more direct, one of them may have more tolls, one of them may go past Granny's house that you want to stop at and get some apple pie. All right, so that's what a graph is. A tree, on the other hand, is typically drawn as follows. So you'll have some kind of top of the tree, which we call root, because we are insane people. And then from there, the tree will branch off into however many branches there may be, and each of those branches will branch off. But the important part is that none of those branches will connect back to a previous branch. So once you start at the root and you go down the tree, as it were, in this direction, you're getting further and further away from the root. You're also getting out to what we call leaves, which are what are on the ends of the branches. Now, you might be thinking, how much has Enda had to drink today that he's drawing a tree like that? Because last time I checked, trees are supposed to look like this, where the root is down at the bottom of the tree and the leaves would be up at the top of the tree. I just want you to know that the fact that I am drawing is really telling you that we're at the end of the semester, and I don't care what you think of me anymore, because I can't draw. See, it's a happy little tree, just like Bob Ross. Okay, so root is the bottom in the real world. When we draw it from a computer science standpoint, we draw root at the top, because we are crazy, insane people, and we draw the trees upside down. Just go with it. Every time you see a tree drawn in a computer science context, it will be upside down. So there you have it. All right, so root is going to be at the top. The leaves are going to be at the ends of the branches, and the branches, of course, are going to be the things that go in there. The important part is the branches do not connect back to each other, creating cycles. If they did, it would be a graph, not a tree. So, in general, all trees are graphs, but not all graphs are trees. That is an important point. It is written on this slide. It is something you should probably remember. I have a premonition of a multiple choice question that will be on a final. That is a common question that people ask. All trees are graphs, but not all graphs are trees. All right, so how do you do algorithms to get around these weird data structures? Well, the answer is our good old friend recursion. If I'm being honest with you, anytime that you need to search or traverse a tree or a graph, you're probably going to use recursion. If you're not, it's going to be very, very painful. And the reason is because, as you probably noticed when we did the recursion module a couple of weeks ago, or what seems like about 6 years ago at this point, but anyway, as we did that, you probably noticed that the code that you wrote was very, very small, simple code. There was 12 lines or less, and magically it was doing this big, complex thing. And that's the beauty of recursion. You just have to solve the simplest problem, and then you let the recursion deal with all of the other stuff. So when you're looking through a tree, that's what you're going to do. You're going to say, is it here in the current node that I'm looking at, or the current leaf that I'm looking at? If not, then recurse and go find it in some other direction. So recursion is going to be what you're going to use every time you're searching a tree, or a graph for that matter. All right, so these are examples of graphs. Graphs can have multiple references in and multiple references out, whereas tree nodes only have one reference in and then typically multiple references out. Graphs can be directed or undirected, and they can be cyclic or acyclic, trees being acyclic. All right, so a tree has a single parent, 0 or more children. A node with no children is called a leaf. The topmost node is called the root. And you can have binary trees, or you can have n-ary trees. All right, so let's talk about n-ary trees. N-ary trees are where you have each node can have n children, just like families, right? Except that instead of one root, you probably have 2 roots if you have children. Or at least at one point there were 2 roots when you... We're not going to go down this path any further. All right, so kind of like a family, you can have an unlimited number of children, and each of those children will then eventually grow up to have some unlimited number of children as well. The starting point is going to be at the top. A binary search tree is one of the most common ones of these examples that you're going to run into. A binary search tree is a tree, has that right there in its name, so we know there's no cycles. It is binary because each node can have at most 2 children. And it is a binary search tree because there are particular rules about how you put things into the tree. Rather than me sitting here and drawing terrible pictures, I'm going to go find the very nice example, which apparently is here. There we go. All right. So you can grab the URL from up here and play with this yourself, but I'm going to start off and I'm going to create an empty tree. This is going to be a binary search tree. It's going to store numbers in each one of the cells. So I'm going to start off and I'm going to insert the number 50 into the tree. All right, and what you're going to see is it's going to create a node, and that node has the number 50 in it. Here's the rule of a binary search tree. Every node can have up to 2 children. If the value that I'm trying to put in is less than the value of the node that we're currently looking at, then I'm going to go to the left. If it is greater than, then I'm going to go to the right. And I'm always going to insert where there is currently a null. So technically there is a null hanging off on the left and the right of this 50 right now. You don't see them because it doesn't draw them because of the way it does it. But I'm going to go ahead and insert number 26. You can tell that 26 is less than 50. So it's going to put it to the left of the 50. It starts looking at the 50. It says 26 is smaller, so it's going to go left. I'm now going to add in 75, which is greater than 50, and so you can tell that's going to go to the right of 75. At this point, the tree is actually considered full because the first node has 2 children, which is the most a binary tree can have, and each of those has no children. All right, so now we can go ahead and insert something else. I'm going to insert the number 10. All right, so 10 is less than 50, so we are going to go left. 10 is less than 25, so we're going to go left. So 10 is going to get inserted all the way to the left. All right, this time we're going to insert 30. Randomly picked at that time. So 30 is less than 50, so we're going to go left, but 30 is greater than 26, so we're going to go right, so it's going to put it over here. All right, so it checks 50, it's less, checks 26, it's greater, puts it to the right. Okay, if we were to then add in 60, that'll be greater than 50, but less than 75, so it goes to the left of 75, and then I'm going to add in 100, and that's going to be greater than 50, greater than 75, so it's going to be out to the right. And again, our tree is full, and so on and so forth. So I'm just going to keep adding in numbers. I'm actually just going to do whatever random number it picks. 88 is going to be greater and less than the 100. I'm going to insert 81. It's greater than 50, greater than 75, less than that, less than that, and so on. So you can tell that there was no rule that said that I had to put them in 75 is greater, less than, greater than. 13 is going to be less than 50, less than 26, greater than 10, and so on and so forth. And you can play with this yourself. I'm going to put in the number 5 just so that you see less than 50, less than 26, less than 10 goes over there. I'll do 83 just so that you see a more complex one. Greater than 50, greater than 75, less than 100, less than 88, greater than 81. It's to the right of 81. Okay, so this is a binary search tree. When you insert numbers, you put them always at the bottom of the tree. They will always be to the left if you are trying to put in a smaller number, to the right if you're trying to put in a larger number. And those are the rules. So binary search trees allow for fast insertion and fast removal of numbers. This is the advantage of doing this, and I'm going to explain this bit in just a second here when the screen renders. So they are specifically designed for being able to search quickly, which is why they're called binary search trees. They are trees, no loops, they are binary, 2 children, and they are search because they are optimized for search. A binary tree consists of 2 nodes, each of which has 2 child nodes. All nodes in a binary search tree fulfill the property that descendants of the left Descendants to the left have smaller values. Descendants to the right have larger values. All right. So here's another example that they're giving you in the slides. Inserting 15 and then putting in 25. You can see that from 15, when we go into insert 25, my pointer's not on. All right, we start at 15. When we go to insert 25, it is greater than 15, so it goes in here. When we go to insert 8, it is less than 15, so it goes there. When we go to insert 4, it is less than 15, less than 8. When we insert 10, it is less than 15, greater than 8. That's why it ended up here. 30, greater than, 20, greater than, less than, 6, less than, what? 6 is less, ooh, what is happening? 6 is less than, greater than. Okay, so I think you get the general idea of how you insert into a binary search tree. So as time goes on and more items get added into the tree, there's an interesting property about being able to search in the tree, which is why we talk about binary search trees as being much more efficient. So at this moment in time on this example on the screen, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 nodes. There are 13 nodes in there. And I would like to search for the number 30 in this tree. So how many nodes am I going to have to look at to search for the number 30? Well, I know that this is not 30. So using recursion, I'm going to go to the left. The reason I know I'm going to the left is because 30 is less than 50. So one operation was to check, is this 30? It's not. I'm going to recurse left. Is this 30? It's not. But it's greater than that, so I'm going to recurse to the right. Is this 30? Yes, it is, and I found it. So search, go left, search, go right, boom, there it is. How many operations did it take me to find the number 30 in this tree? Well, presuming that searching a node is one operation, then effectively I had to do 3 searches to find it. Let's try searching for the number 81. 1, 2, 3, 4, 5. You can tell that the worst case scenario would be if I had searched for 83, in which case it would have taken 6. But again, there are 13 entries in this tree. 6 is not great for 13. I had to check half of them. But that's the worst case, is that I had to check half of them. If the tree is nice and balanced, and I'll explain balanced in just a moment, so I'm going to ask for it to make me a new tree. There it is. And I search for any number in this tree, such as the number 50. 1, 2, 3. Found it. No matter what number I pick in this tree, the worst case scenario is that it'll take 4 operations. That's pretty impressive considering that there are 2, 4, 6, 8, 10 entries in this tree. And the reason for this is because of the way that they're organized. Every single time that I make a decision, I get to discard half of the tree. What do I mean by that? So I'm going to search for the number 1, which we know is not in here. But let's go through it ourselves. So we're going to start at the number 41, which is the root of the tree. And we're going to see, is 1 equal to 41, which it's not. At this point, I can conclude definitively that everything to the right of 41 is irrelevant. I can throw away the entire right-hand side of the tree. The 41, the 65, the 50, the 91, the 72, and the 99. I know it's not over there. So I have eliminated half of the choices, approximately, on my very first decision. I then go left, because I know it's less than 41. So now I'm at the node 20. So now I'm going to say, is 1 equal to 20? It's not. Okay? So is it less than or greater than that? We know it's less than. So again, I get to throw away half the tree. I get to throw away the 20, the 29, and the 32 because I know it cannot be over there. And I go left. I'm now at 11. And again, I check to see is 11 equal to it. It's not. I try to go left. There's nothing there. I know 1 is not in the tree. At each point, I was able to throw away half of the options. Let's play a guessing game. I'm going to think of a number in my head, and I want you to try and guess the number. The number is going to be between 0 and 100. Okay, there is a correct way to play this game if you want to be as efficient as you possibly can be. Assuming that I will tell you whether the number that you guess is too high or too low, which is an important thing. But if I am willing to tell you that, then the correct first guess that you should make is the number 50. Because no matter whether or not you're correct, I'm going to get rid of half of the choices for you. If you are correct, great, whoop-de-doo, you're very smart. But if I tell you that the number is less than 50, then you know that you can eliminate 51 through 99, or 100, or however far we're going. At that point, there's another correct guess for you to make, which is 25. Because, again, no matter what, you're going to be able to throw away half of the choices. And then you should either pick halfway between 25 and 50 or halfway between 0 and 25, depending on whether I tell you it's greater than or less than 25. And at each point, you should half the difference. This is called a binary search. And if I am telling you whether or not your number is too high or too low, then a binary search is the most efficient way for you to get to the answer. So remember this when you're doing a drunk game. A binary search tree implements that idea in a tree. Every time that you make a decision, you get to throw away half the tree. So it is stated that searching for an element in an array means that you have to look at every single element in the array. If the array is of size n, then it's order n in order for you to find one item in the array. Likewise, if it is a linked list. If I tell you that the array is sorted, then you now have greater than less than, because you can look at the element right in the middle of the array and you can see whether it is greater than or less than the value that you're looking for. And since it's sorted, that allows you to throw away half the choices. So a sorted array or a binary search tree allows you to do a search in what's considered order log n time. Okay, that's one we haven't seen before. So we've seen order 1, which means that I can do it in effectively one operation, but in reality in a constant number of operations. Regardless of the size of the array or the size of the data structure, I can find the answer in a concrete number of searches, in a deterministic number of searches. It'll always be 1 or 2 or 3, regardless of the size of the data. That's order 1. The other one we had talked about up until now was order n, which meant that as the structure grows, I'm going to have to do more and more work. I'm going to have to do approximately n work in order to find it. And that was searching in an array or searching in a linked list. As I just said, searching in a binary search tree or searching in an assorted array is considered order log n. And the way that you can always know that something is log n is if I ever tell you get to throw away half the options at each choice. That is going to be log n. Now you might be thinking to yourself, when you say log n, what do you mean? I literally mean the mathematical term log. So if you're familiar with exponential growth, so something that is growing exponentially looks like that on a graph, right? It happens very, very quickly. Versus something that linearly grows, it happens very smoothly. Logarithmic is the inverse of exponential. So in the case of a tree with 100 items in it, if I try to answer the question, how many searches am I going to have to do in a tree with 100? The answer is log base 2, because it's binary, of the number. So I don't care that you understand the math of this. We're just going to use a little calculator over here. So if there are 10 items in my tree, in my binary search tree, and I try to search for one item in there, it will take at worst 3.3 queries. If I put 100 entries in the tree, it will take at worst 6 queries for me to get to 6.6, so 7, I guess, for me to find the item in there. With 1,000 entries in the tree, it's It's log base 2 of 1,000, which comes out to 9. Now you can tell that this is dramatically better. So if I had to search for an item in an array, and the array is not sorted, then I'm going to have to look at all 1,000 cells at worst case scenario. The moment I tell you that they're sorted in a binary search tree or sorted in the array, I can find the item in 10 queries for 1,000 students. KSU has 40,000 students. So there is a data structure somewhere that has all of y'all's information in it. I can find any one student in that data structure in 15 queries, as long as it's in a binary search tree or a sorted array. That is way better than having to do 40,000 queries. Way better. And you might say, I don't care, my computer's really fast, who gives it? Well, the answer is that not every time that your code is running is it going to be on the fastest computer out there. So somebody may need to run your algorithm on a Raspberry Pi or something smaller than a Raspberry Pi. And it still needs to be efficient. 40,000 operations versus 15 operations is a big difference. And this is only for a data set of 40,000. In reality, how many students have ever been at KSU is probably a lot closer to 500,000. Or maybe more than that, I don't actually know. For 500,000 people, I can always find the answer in 18 operations. So, in big O notation, which is what we are talking about here, there is order 1, which is the best case scenario. It is a constant amount of work no matter what to find something. Order log n is the next best thing from order 1. Order n is the next best thing. And it does get worse past that. We're not going to really talk much about those algorithms, but there is such a thing as order n squared, order n to the n, and order n factorial, all of which are very, 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 very bad because they have lots and lots of work that they got to do. So, binary search trees are a way in which you can store data in a way that is easy to search. It is optimized to search. It takes a little bit of effort to put them into the tree. You always have to look at each thing and decide less than or greater than. You can see in this example, the data doesn't always have to be numbers. It could be letters. So these are sorted by the first letter. So J to E to A to H, or J to R to T. That's sorted by strings. And that will be a common way to do it as well, where you're organizing it by the order of the strings. As long as you can order the things, it doesn't matter whether they're numbers, strings, characters, or whatever else. So, adding each node, ideally, you want your binary search tree to be relatively balanced. What does the word balanced mean? So I'm going to create a couple of random trees. So this is a random tree. You can tell this is not balanced. The 90, which is the root of the tree, has no children on the right. Everybody ended up on the left. That's not great. Let's pick another random tree and let's talk about that. Again, everybody ended up on the left. Not great. Let's do another one. Okay, that one's fairly balanced. There's about the same number of kids left and right. That's what you want. You want a balanced tree. So I can very specifically ask for a balanced tree, and it will give me a random balanced tree every time. That is pretty close to balanced. It's not exactly balanced because obviously the 20 has one child on its left, but it has two descendants on its right. They're not both children. One's a grandchild, but it's pretty close. So that's considered a balanced binary tree. Now, why does this matter? Okay, I'm going to give you a binary search tree. I'm going to insert the number 10 as the root. Then I'm going to insert the number 20, which is going to go to the right of that. Then I'm going to insert the number 30. Well, where's that going to go? Well, it's going to go to the right of the 20. Then I'm going to insert the number 40. Where's that going to go? Well, it's going to go to the right of the 30. Okay, are we sure this is still a binary search tree? Yes, I'm still following all of the rules of a binary search tree. I'm always putting larger numbers to the right and I'm putting smaller numbers to the left. The only thing that has changed is that I'm giving you the numbers in sequential order. Regardless of whether they're ascending or descending, they're coming to you already in order. This is the worst case scenario for a binary search tree. Because how many operations is it for me to tell you whether 51 is in the tree or not? Well, it actually ends up being n. I actually have to start at the 10, and then go right, and then go right, and then go right, and then go right, and there are 5 entries in here, and it took me 5 to get you your answer. The worst case is n. But Enda, you told me just 10 seconds ago that binary search trees are log n, and that they're great, and that they're wonderful, and now you're telling me that they're not great. Why are you messing with my head? Well, the answer is binary search trees are log n as long as they're balanced. If they're not balanced, they're no longer considered log n. At that point, they're considered order n. So it's very important that they go in balanced. And you might say, okay, but how do I guarantee that they're going to come in balanced? Because if we take the student IDs for every one of you, when you were added to KSU, you were given a what are they called? KSU ID. So each one of you were given a KSU ID. I don't actually know how they're done, but I assume they're sequential. I assume that the next student coming in gets 1 plus the previous one. So if you insert the students sequentially, which is exactly how they would be based on their KSU ID, you would end up with a very, very unbalanced tree. So what to do? Well, all I'm going to tell you is go take a data structures class and you'll learn how to solve all of this. But the very high level version is there are a couple of options. One is something which is called tree rebalancing, where you do an operation to rebalance the tree. Because you can have a binary search tree with the same numbers in it that looks very different. This is 10, 20, 30, 40, 50, right? I'm going to clear the tree, and this time I'm going to insert 30 first. And then I'm going to insert 20, and then I'm going to insert 40, and then I'm going to insert 10, and you can tell that already this tree is much more balanced. It's the same numbers, but it's better. 50 was the last one. Okay, so it's still not perfect, but at least it's much more balanced than it was before. These are the same numbers that were in it the other time, I just gave them to you in a different order. So it is possible to rebalance the tree, which means twisting it around until you get back to a more balanced. There are a number of different ones, AVL trees, red, black trees, B trees, all of which allow you to do these kinds of things. They will all be covered in a later class. None of that is relevant for here. I just need you to understand that a binary search tree can be balanced or unbalanced. As long as it is approximately balanced, you get order log n for searching. Inserting, order log n. Deleting, order log n, because it is all the same work no matter whether you're inserting a new node, deleting a node, or taking or searching for something in there. As opposed to an array where if it's not sorted, it is order n to search for something in there. It may be order 1 to put in and order 1 to take out. It's probably order n to take out because you're going to have to search the array to find the thing you want. So log n better than n. That's the important part here. I think you've seen from the numbers that it makes a tremendous difference once you get to large numbers of nodes in there. In order to gain that, you have to be balanced when you start off. Okay, tree traversal schemes can be pre-order, in-order, or post-order. In all 3 cases, it is a very simple block of code. So your code is going to be, and we're just going to take a look at this from the top, searching or printing out all of the entries in the tree. I'm going to do an in-order traversal of the tree. The code for this is you are going to begin by recursing left, then printing the current node, then recursing right. Okay, so I'm going to recurse left, I'm going to recurse left, I'm going to recurse left. Okay, I have done my 3rd recurse left. I am now at a point where I can't recurse left. So the next step in the algorithm was to print. So I'm going to print out the number 2. Now I'm going to try and recurse right, which I cannot do. So this is now done on the stack, and we're going to go back up to here. What we had done up here was we had recursed left. That's already done, so now it's going to do the print, which is going to print out the number 4. And the last step that it's supposed to do is recurse right. From here, it's going to try and recurse left, which it can't do. It's going to print, so you're going to get the 6, and then it's going to try and recurse right, which it can't do. So it's done, and it's going to pop off the stack. This guy is done because it went left, it printed, and it went right, so it's going to pop off the stack, and we're back up to here. All right, he had gone left. Now he needs to print, so he's going to print the 8, and then he needs to go right. So he goes right. He's going to go left. He's going to try going left, can't. He's going to print, and he's going to try going right. So he printed the 9, and we're back up to here. He went left. He's going to print, so we get the 10, and now he's going to go right. He's going to try going left, can't. He's going to print, you're going to get a 12, and then he's going to go right, which he can't, so he's done. He has gone left, he has printed, and he has gone right, so he's done. He has gone left, he has printed, and he's gone right, so he's done. We're back up to here. This guy has gone left, so next job that he should do is to print, so we get a 15, and now he needs to go right. And I think you can see how this is going to continue. This guy is going to go left, left, print, try to go right, can't. Back up here, print, try to go right, try to go left, can't, print, try to go right, can't, done, done. He's gone left, he needs to go right. Sorry, he needs to print, then he needs to go right. He's going to go left, he's going to try going left, he can't. He's going to print, he's going to try going right. He has gone left, he needs to print, now he's going to try going right. He's going to go left, which he can't. He's going to print. He's going to try going right, which he can't. He's done. He's gone left and right. He's gone left and right. He's gone left and right, and we are done. That is an in-order traversal. And you can see that the in-order traversal will give you back from a binary search tree the numbers in order. The code was nothing more than if temp equals null, then return. Otherwise, recurse left, print, recurse right. That code gives you an in-order traversal of a binary search tree and will print out the numbers in order. Just going to do one more example. I'm going to pick a random tree. Okay, I'm going to pick a balanced tree just so that you don't have to. And I'm going to do an in-order traversal. Starts at root, goes left, can't, prints, goes right, and so on and so forth. Again, this site is really cool because it gives you a visualization of how it's doing it. The little caret that you can see underneath each of the items tells you where it is in the code, and flashing underneath the window where my little screen is here, you can actually see it running the code and telling you which way it's going and what it's doing. And you can see the output on, it's on here somewhere. I think it's underneath the window where I am. So I'll let you go play with that. That's an in-order traversal. There is also something called a pre-order and a post-order. The only thing that's different is where the print statement is. In an in-order, the print statement was sandwiched between the go left recursion and the go right recursion. So it was go left, print, go right. That was in order. A pre-order, as the name suggests, prints, then goes left, then goes right. A post-order goes left, goes right, and then prints. So the name just tells you where the print statement goes. So I'm going to just briefly show you what happens with a pre-order. So in a pre-order, the first thing that happens is it prints, then it goes left. Print, then go left. Print, then go left. Print. So you can see you get 15, 8, 4, 2. At that point, it tries to go left, can't, go right, it can't, so this one pops off. This one has printed and gone left, so it goes right. It's going to print the 6 at that point. It's done, it's done. It has printed and gone left, so it's going to go right. Now you get the 10. It's going to print, go left, print, go left, can't, go right, can't, done. It's already printed and gone left, go right, print, left, right, done, 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 go right, and then continue its way down the path. That was a pre-order. A post-order, left, 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 can't, print. Print, 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 print. In a post order, the root is going to be the last entry. In a pre-order, the root is going to be the first entry, and in an in-order, the root is going to be somewhere in the middle. Depends on how balanced the tree is. The first two are always true. Post-order, the root should be at the end. Pre-order, the root should be at the front. In order, it's going to be somewhere in the middle, depending on how balanced the tree is. All right, so the algorithm in each case is going to have a recursion left, a recursion right, and a print statement. The order of those determines which one you get out of a binary search tree. All right, and this is your code. Okay. A tree, we haven't really talked about the structure here of how you would make it, but we still have a node, just like we had for a linked list. The only thing that's different is there's going to be a left pointer and a right pointer. I'm calling them pointers, they're just links. That is very similar to what we had for our next. We're just going to have one called left and one called right. Again, there's nothing magical about them being called left and right. That's not what makes them be the way that they are. The only thing that makes them be who they are is simply the fact that you're putting the data on the left or on the right, depending on where you're going. Okay, so taking a look at this screen here, this is from a game. And the question is, what are you looking at? Is this a tree? Is this a binary tree? Or is this a graph? So you can see that the root is this guy up here, the nexus guy. All right, and he appears to have a child this way, a child that way, a child this way, and apparently a child that way. So I can tell straight away that this is not a binary tree because there are 4 children of this guy. 1, 2, 3, 4. And then this guy has 1, 2 children. So he conceivably would be a binary tree. But this guy is not a binary tree because he has 4 children. And then this guy has 1 child. So the answer is this is not a graph because at no point does anything connect back to anything else. But it is a tree. It is not a binary tree. This is an n-ary tree. In this case, it will be a tree of 4 is the most that I can see here. So instead of binary, it will be a 4-way tree where each node can conceivably have 4 children. It is possible it is 5 or 6 and I just don't see it because I haven't seen enough of the tree. This is an example of a graph. How do I know it's a graph? Because if I start off at the mall and I go south to Metro Central, and then I go left from there, okay, sorry. I had looked at this earlier and I did have a path that was a circle. There is at least one circle in here. All right, Metro Center up to Penn Avenue to Pennsylvania, Pennsylvania to Penn Avenue, the other one to Georgetown, Georgetown down to G-Town Mall Metro, and then that connects you back down to Metro Central. So there you go. That is a loop. This is another loop. So that is definitively a graph because there are loops in there. So that's how you can tell whether something is a graph or a tree. Okay, so that brings us to the end of the slides. Let me wrap up with the things that are important for you to have gotten out of today's lecture. Graphs have nodes that are connected to multiple nodes. Graphs may or may not have cycles. Trees have a structure such that there are no circles. Everything is just descendants of everything else. Your file system is a tree. On your computer, when you open up your file explorer, you have the C:root if you're on Windows, or you have /user/ whatever your name is if you're on Linux or a Mac. And in there you can create any number of folders, and those folders can have folders, which can have folders, which can have folders. That is a tree. It is impossible, pretty much, for you to create a cycle in there where anything inside would connect back to something else. I say pretty much because there is such a thing as a junction in Windows and a symlink or a hard link in Linux and Mac. But for the most part, what you're used to in everything that you've ever dealt with in your life, it is a tree. You have folders, which can have folders in them of any number. So it's an n-ary tree, not a binary tree. You can have more than 2 folders inside a folder. And then each of those folders can have folders in them and or files in them. That is an example of a tree. A graph is something where you have connections. Both of them are real-life things that exist in the world. Trees are a very common way of organizing information. Your family tree is a tree. You have parents and then children and grandchildren, and you can see relationships between various different people. So trees are a way that you organize people. They're a way you organize files in a file system. They're used by many different things. Binary search trees, very specifically, are used throughout computer science because they're a very efficient way of storing information and being able to search for it or retrieve it very quickly. With the caveat, the binary tree has to be balanced in order for that to work. Big O notation, which we have now covered in 3 separate lectures, is a way of measuring how much work it is to find something or do something in a data structure. You've so far seen order 1, which is the best case scenario. You can get to something very quickly in a constant amount of time. Order log n is the next best thing, which is a binary search tree searching through an array that's already sorted. Order n is the next best, which means you just have to look at every single node, and the amount of work that you do grows proportionate to the amount of data that you're having to store. Past that, as I briefly mentioned, there's n squared, n to the n factorial, which are all worse than those, and you will run into them when you do sorting algorithms to reorganize things inside of an array. I want you to be aware of big O notation. Again, whole class going to cover that later on in your career, but you should at least have a vague understanding of what it is and how it's used. You should definitely know order n versus order log n versus order 1 and why you would use a binary tree. We're not asking you to code a binary tree. We're not asking you to code linked lists, with just the exception of being able to traverse them or something along those lines. So you should know how to do it, but it's not that's not the primary focus here. The primary focus is for you to understand how they work, how you use them, and whatnot. If you guys have any questions, you've got at least 4 more office hours before we hit Thanksgiving. There's going to be a review video during the week between Thanksgiving and the final exam, and then the final exam will be 2 weeks after Thanksgiving. The exact date on that has not been decided yet, so I can't tell you that, so look out for announcements as we get closer. But it is not the week of Thanksgiving, it is not the next week, it is the week after that, probably on the Monday, Tuesday, or somewhere in that range. I don't actually know the schedule, so don't hold me to that. By all means, send me emails if you have questions or you want to ask anything about anything we have covered, whether it's trees, graphs, linked lists, data structures of any form, big O notation, or anything from earlier in the semester. I'm always here in office hours. Feel free to stop by and ask questions, and I will see you in the review when we do that in a couple of weeks. I hope you guys have a fantastic Thanksgiving if you're watching this before Thanksgiving. Try to relax and enjoy. First break that we get this semester, it's fantastic. This is all the material, so if you haven't jumped out a window so far, then life is good, because there's no more new material. After this, we're just going to review everything that we have covered. So you've officially made it through 1322 if you are watching this video, minus 1 final exam, which you're going to take and you're going to ace because you're awesome. You guys have a lovely night and weekend, and I will